Welcome students to this series of lectures on statistics. And within this series of lectures on statistics, we are currently studying probability distribution. And within probability distribution, we are focusing on discrete probability distribution. Cool. Till the last session, we completed Bernoulli distribution and binomial distribution. And in this session, we'll try to complete Poisson distribution. So in this session, we'll introduce the Poisson distribution and we'll try to also understand the probability mass function of Poisson distribution. Now, if I try to explain Poisson distribution in one line, in just one line, then Poisson distribution you can use, or it should be used when you are interested in finding the probability of certain number of events occurring in a fixed time interval, occurring in a fixed time interval. For example, you are interested in what is the probability of 2 defaults in a year? What is the probability of 20 defaults in a year? What is the probability of 10 accidents in a month? What is the probability of 5 accidents in a month? So you're interested in 5 accidents, 10 accidents, but in a month. Okay. What is the probability of 5 phone call arriving at a call center in an hour? Or what is the probability of 20 calls arriving at a call center in an hour? So if you're interested in the number of events in a fixed time interval, then you can use Poisson distribution. So whenever the question is about probability of a certain number of events, probability of a certain number of events occurring within a time interval, we use Poisson distribution. Now, something very weird is that, and pretty interesting about Poisson distribution is that it is related to what? Time. And time is one of the most continuous entity in the world, one of the most continuous quantity in the world, right? Yet Poisson distribution belongs to the category of which distribution? Discrete distribution. Why? The reason is simple. In this distribution, we are not interested in probability of time itself because that's a continuous entity. Instead, we are interested in the number of events occurring in a given time interval. The number of event is a discrete quantity. It is 0, 1, 2, 3, 4. Very similar to what we did in binomial distribution. And that's why Poisson distribution falls under discrete probability distribution. Now, comes another interesting aspect of Poisson distribution, that is, suppose you want to predict the probability of 100 default in a year for a bank, or probability of 100 credit card payment default in a year for a bank. You can use Poisson distribution only if you already know average number of defaults in a year. If you're not aware of average number of default in a year, you cannot use Poisson distribution. Pretty weird. Similarly, if you want to model accidents in a month or phone call in an hour, you must be aware of the average number of accidents or average number of calls. If you're not aware of average number of accidents or average number of calls, which is the mean value, expected value, or on an average value, you won't be able to use Poisson distribution. Pretty weird. This average value is called as lambda. Okay, this is known as lambda. So if you know that on an average there would be 5 default in a year, if there would be 3 accident in a month, if there would be 5 calls in an hour, you can use Poisson distribution. Okay, so that is your lambda. And if you do not know lambda, you cannot use Poisson distribution. Simple. In very simple terms, before predicting the probability of different possible outcome, 2 defaults in a year, 1 default in a year, 50 defaults in a year, you must be aware of the expected value. You must be aware of lambda. Okay, so the average rate of occurrence of the event should be known, otherwise you will not be able to use Poisson distribution. And what is this lambda? When I say on an average, what is this lambda? This lambda is what? Your mean. This lambda is your expected value. This lambda is your average value. All refers to the same concept, different jargon, different terminology. Correct? Okay. Now, the second most important point for using Poisson distribution is that all events, the first was what? Average rate is constant and it is known. Now, the second most important point for using Poisson distribution is that all event should be random and independent. Random and independent. There should be no relationship. There should not be any relationship, or there should be no relationship between the first event and the second event. Now, you might feel that this sounds similar to the binomial distribution, and you would be correct. In fact, Poisson distribution is derived from binomial distribution. Is derived from binomial distribution. Okay. And in this session, we'll see how probability mass function of binomial distribution can be used to derive the probability mass function of Poisson distribution, or how it converges to Poisson distribution probability mass function. In many ways, you can say that the binomial distribution can be considered the mother of all the distribution. Okay. Under certain condition, the binomial distribution tends to Poisson distribution. It will converges to Poisson distribution. And in other condition, it can also converges to normal distribution. Similarly, Poisson distribution itself converges to normal distribution, okay, under certain conditions. So if you understand binomial distribution properly, deriving other distribution becomes very simple and easier. That's why we took a lot of time to understand binomial distribution. Okay, with that, let's introduce our probability mass function. Probability mass function of Poisson distribution. We are introducing what? We are introducing the probability mass function of Poisson distribution. What is that? Lambda raised to the power k. What is lambda? Lambda is that on an average value in an interval. K, number of events you are interested in. Are you interested in 2 events? Are you interested in 5 events? Are you interested in 6 events in an interval? E is a Euler constant. So if you're aware of lambda and k, because E is a Euler constant, which value is 2.71828. Okay, I'm repeating that lambda is what? Lambda is the expected value, is the mean, is on an average value or on an average number of events in a given interval. If these values are known, you can use Poisson distribution. Otherwise, you cannot use Poisson distribution. We already discussed that. Okay, so lambda should be known. The formula tells us that if you're interested in probability of k events occurring, and you know on an average number of event in that interval, like 5 defaults, 3 accidents, and 5 call, then you can use this formula to find the probability. Okay. And since all the values are known, you simply have to what? Substitute the value into the formula, put the values into the formula, and you will obtain the probability. You will have the probability. For example, you are interested in finding 4 defaults in a year. How many defaults in a year? 4 defaults in a year. So K would be 4. And you must be aware of the average number of default in a year. What is the average number of default in a year? 5 default. So K is 4. K is 4. Lambda is 5. E is a Euler constant, that is 2.71828. You just have to substitute the value and get the probability, right? Okay. So this is very simple. Suppose you want to find the probability of 3 accidents in a month and the average number of accident per month is 5. Then lambda is what? 5, and your K is what? 3, and E is a Euler constant which will remain constant. Okay. So let's take a very simple example and try to solve this example at your end. Pause the video and try to solve it. I'm reading the example for you. Suppose a hospital receive 3 emergency cases per hour on an average. As you read the sentence, you find on an average, then it refers to what? Lambda. This is our lambda. So lambda is known. What is the probability of receiving 2 cases in an hour? You are interested in 2 cases, 2 event. So K will become what? 2. So you put down the value of K equal to 2. Lambda is what? 3. Lambda is 3. E is a Euler constant, 2.71828. And at the end, you will get the probability as 22.4%. Okay. Now, suppose you're interested in some finance application or Poisson distribution. And I'm just taking a very simple application. If you're investing in, say, 100 stocks, that is your investable universe, and on an average, 5 stock rises in value every hour. What is the probability of 100 stock rising in an hour? So what is your lambda? 5. What is your K? 100. What is E? 2.71828. You substitute the value in this formula and you will get the probability. Okay. But the important question is how we achieved or how we got this probability mass function of the Poisson distribution. What we know that lambda need to be known. Otherwise, you cannot use Poisson distribution. Perfect. And as I mentioned earlier, that binomial distribution is the mother of the Poisson distribution. So binomial distribution will lead to Poisson distribution. The probability mass function of the binomial distribution will converges to. So this is the probability mass function of binomial distribution. Remember, ncx p to the power x q to the power n minus x. That will converges to lambda raised to the power k e to the power minus lambda k factorial. K or x would be the same stuff. Either you say k or x, it doesn't matter. But when it converges, there are certain conditions, and actually two conditions. I've written three, two conditions. If you remember when we were playing with binomial distribution, n was what? Limited, finite, n was 5 in our example. We were tossing the coin for 5 times. If you have many trials, huge number of trials, like in 1000, 10,000, 1 lakh, very near to infinity, then you can use Poisson distribution. If the probability of success is very bleak, the probability of success is very, very small, not like 0.6 in our previous example of tossing the coin, where the probability of success was 0.6, probability of head was 0.6. If the probability of success is like 0.00001, you can use Poisson distribution. And if you remember, what was the mean in the binomial distribution? The mean in the binomial distribution was n into p, right? We derived it. We derived the intuition behind that, n into p. That was the mean of binomial distribution. What is the mean in Poisson distribution? That is lambda. So either you call it as n into p or lambda, it doesn't matter. But what is important? N is a very large number, p is a very small number, so lambda is a reasonable finite number. That is a very important point. Lambda should be like a finite number. Lambda should not be like unreasonable, like 0.0001, or it should not be like infinity. So it's a finite, easy, rational number. Okay. If all these conditions satisfied, you will see that ncx p to the power x q to the power n minus x will converge to this probability mass function. Few things that you have to do. So you will start with ncx p to the power x q to the power n minus x. First do this. You know lambda is equal to np. Replace p with lambda upon n. That's all. As you replace p with lambda upon n, something will start happening. The second thing that you have to do, you have to expand ncx. As you expand ncx, you will find that n minus x factorial and n minus x factorial will be cancelled from numerator and denominator simultaneously. So you will cancel it out. This is one. After this, what you need to do is you have to take n common. So as you take n common from all the entity from the numerator, the number of entity will be x. You can count it. So the number of entity would be x. Then if you take n common in every entity in the numerator of ncx p to the power x, sorry, ncx, which is n factorial after cancelling out the numerator and denominator, then you will have n raised to the power x here. And you remember you did lambda upon n instead of p. So you will have n raised to the power x in the denominator. They will cancel out each other. Now the most important stuff that you should remember, that n is very near to infinity. If n is very near to infinity, so these value 1 upon n, 2 to the power 2 upon n, 3 upon n, x minus 1 upon n in the numerator will become 0, and it will become 1, it will become 1, it will become 1, it will become 1. Each entity will become 1. So you will left with 1 upon x factorial, lambda raised to the power x, and you would be left with 1 minus lambda upon n raised to the power n minus x. I'm just writing x in the denominator because the power is minus x. Now here limits n tends to infinity make it e to the power minus lambda. This is a differentiation and integration very famous formula. It will make it e to the power minus lambda. And again here n is what? Very large. This will become 1. So it will tends to 1. At the end, you will get the probability mass function of Poisson distribution. Now this is not required, but I want to just give you a glimpse that how you derive the probability mass function of Poisson distribution. It derived from the binomial distribution itself. And then the question would be, what is the mean of Poisson distribution? It is lambda. What is the variance? It is also lambda. How you can find the variance? Integration of probability into x minus mu raised to the power 2. If you do that, you will get the variance as lambda. I don't want to enter into the derivation of variance, but now you have a method to derive the probability mass function of Poisson distribution and variance of Poisson distribution. Okay, with that, I'll end the session. Thank you. Have a nice day.